Well, hello everyone, and good morning from Vancouver. I'm Akua from Edumine, and I'd like to welcome you to the Managing Tailings Through Satellite-Based Technology webinar presented by PhotoSat. We encourage you to participate in the webinar today by asking questions. You can do so by using the Q&A tab at the bottom of your screen. There will be a dedicated time at the end of the webinar to answer any questions you may have. Thank you for listening and participating in today's webinar. We will now get things started as I pass things over to our presenter for the day, Sam Rivet.
Thank you for the introduction. And I'd like to thank you all for joining me today. My name's Sam Rivet, and I'm a sales engineer here at PhotoSat. I'm a mining engineer by trade. I started my career on site as a consultant or staff for the oil sand operations in northern Alberta. A lot of work on large-scale earthworks projects, dikes, storage pads, road construction. Like a lot of you in the audience today, probably a lot of quality time spent working with survey data, designs, takeoffs, material balances, refining that data, that information into an optimized plan, the scope of work. Conversely, a lot of analysis looking back, using topographic surface data to report on provable volumes of ore moved, waste and tailings to the dike, or verifying, establishing cut quantities for invoicing. In all those projects, in all those situations, the backbone, the singular most important source of information was the survey data. The original ground surface, the current surface, month-end surface last month versus this month. It's the only way to really quantify what the situation is. How much ore did we really move? How much capacity does this dam really have? How much fill will it take? Did it take to construct this structure? These are questions you can only answer with good surveying. And when that survey data was off, outdated, or improperly gathered, it compromised your understanding of where your operation was and inevitably will shape where your operation will end up. The challenge with these vast mining operations, with these massive earthworks tailing structures, is access and scale. You need a large amount of data, you need it everywhere, you need it to be really good, and you need it tomorrow. And you have to gather all that information that you're dialing into the centimeter scale while evading the litany of complications that could lead to errors. This is where we come in. This is what we do. Okay, so in this presentation today, I'm going to cover who we are, what defines a good survey product, how we produce our surveys, what common errors exist out there and where they come from, how we apply our technology to monitor active mine sites, active tailings dams, and how we apply our technology to go back into the past and rebuild the construction history of older legacy tailings storage facilities. Okay, so this is us, PhotoSat. Our expertise in geophysical data processing combined with our extensive experience has resulted in the world's most accurate satellite surveying company. As you can see on your screen, with each orange marker there representing a completed project, we operate all over the world. One of the many benefits of utilizing satellites to gather our data, it's resulted in over 1,500 projects right now in 75 countries. Okay, quick timeline of our history. Founded in 1993 by our president, Jerry Mitchell, initially providing mapping consulting services for resource development. In and around 2005, we were doing our initial surveys by having outside contractors do survey calculations using photogrammetric workstations. We wanted to see if we could help them because, quite frankly, they were taking too long. After our initial efforts, we found our surveys were not only faster, but better. Okay, by 2007, we're now delivering our own satellite surveys for customers. Okay, quick overview of how satellite surveying works. So a satellite, like you can see on your screen, is going to take a picture of an area from two different perspectives, essentially simultaneously. Having those two images that we call stereo pairs of the same area at the same time allows us, given how we process the data, to produce really accurate ground elevation measurements. We use high resolution satellites. We find right now the WorldView satellites give us the best results, so they're our go-to for any operating mine, but we're constantly adding more satellite fleets to our repertoire of information sources. That just allows us to gather more and more data faster and faster. Okay, back to the timeline. Then in 2010, the process evolved using modified seismic algorithms that increased our vertical accuracy on our survey data to 0.5 meters. Beyond that, we wrote all our own software to run off the graphic processing units as opposed to the central processing units, and that really started to optimize processing times. So we were really starting to mesh this data-intensive process that was producing more and more accurate results with optimized processing times, so we could produce, accurate DEMs and turn them around fairly quickly, which is what all our clients want. By 2012, 0.3 meters in vertical accuracy. By 2013, 0.15 meters in vertical accuracy. And today we achieve results that are at or better than 15 centimeters in vertical accuracy, delivered once again, 1,500 projects in over 75 countries. Okay, so you may have noticed that I've referred to our vertical accuracy already a few times in this presentation, even going so far as using it as a benchmark in the history of our organization. That's because it is important, and along with precision, really defines the quality of your survey. Okay, so what is vertical accuracy and precision as it relates to survey data? Okay, so imagine the bullseye is the exact location of the point you're trying to survey. It's the truth. Those blue dots, those are your attempts at surveying that bullseye. Okay, in that first target on the left of your screen, the blue points are all on the target, but they're all over the target, all fairly close to the bullseye, but inconsistent in their proximity, in their proximity to each other. This represents, good vertical accuracy, but low precision. Okay, in that second target in the middle, those blue dots are all off the target, nowhere near the bullseye. However, they're tightly clustered together, very consistent. This represents good precision, but low vertical accuracy. Then on the right there, you guessed it, good precision, good vertical accuracy. You're on the bullseye every time. Ideally, this is what you'd want, and this is what we strive for. This is what we produce. But depending on the application, having one or the other is going to be imperative. Like if you're trying to locate a buried line on your site, it's buried 3 meters deep, you have an as-built, you're going to need good accuracy, good vertical accuracy. You need to physically locate that line in real time. But if you're comparing, two surfaces against each other, month end from one month end to another, you're trying to determine the relative difference, the amount of ore moved, you're going to need good precision because it's the relative difference that matters. So precise but not accurate, accurate but not precise. Okay, so when I refer to a vertical accuracy, this measures an average. The average in question is the root mean square error. It measures how much error there is between two data sets. In our case, the two data sets would be the new survey we produce versus a known absolutely accurate survey in inactive areas. The residuals, those green arrows on your screen, that's a measure of how far from the regression line the data points are. So the RMSE is a measure of how spread out these residuals are. The RMSE is a standard deviation on your residuals. Okay, so how do we determine exactly where our surveys stand versus reality? Okay, one of the strengths of our surveying is everything is captured instantaneously in one snapshot. Hundreds of square kilometers surveyed all at once. This enables PhotoSat to precisely measure the vertical accuracy by comparing the new PhotoSat survey to all the existing ground survey data and all the previous surveys for all unchanged areas of your site. You have way more information to reference to make sure you're correct, and all that information is being produced in one continuous data set, and that's important. This adds a level of reliability, of repeatability to the data, and makes it very self-consistent, so very high precision. This allows us to do accuracy studies on our data by studying what we produce versus the supply data within those inactive areas, and we're always picking them up because of the scales of our surveys. Each survey we produce comes with a project report that analyzes the accuracy, the quality of the control, and all relevant technical details. Full transparency. So our clients always know what the specs are on their survey. But not only that, we've published publicly over 50 accuracy reports since 2008. You can download them, you can scrutinize them, analyze them. And to me, in my experience, this is very rare for a survey company to do, particularly a satellite surveying company. But we have the goods. So leading, publicizing the quality of our work is beneficial to us as a business. So to that point, after this quick disclaimer, so this presentation is going to contain real data from real projects that we've worked on over the years. Obviously, these examples are intended to be anonymous unless we have client permission to show. So, if you recognize any sites or any type of the data, please, do not put it in the chat. Okay, so this is 3 years worth of data, the last 36 months of survey projects we produced. We've separated them into 3 different categories, exploration development projects, operating mines, and recurring mines. So recurring mine would be an operating mine that we do multiple times a year. You can see the average vertical accuracy or RMSE for these types of projects. And this is a sample size of hundreds on your screen. So we have, 12.57 centimeters in average vertical accuracy on our projects for recurring mines, 13.26 for operating mines, and 14.27 for exploration development projects. Considering these projects are 25, 50, 100, 300 plus square kilometers, and that we're turning the data around quickly and everything is done completely remote, this is excellent. Now you can get, under 5 centimeters RMSC if you, hand top out something. You could probably get under 10 centimeters RMSC if you carefully droned an area slowly, skillfully. But access, scale, and resources is going to become a problem, and become a problem fairly quickly. If you want this level of scale and quality, you're going to need to probably airborne LiDAR otherwise. But that becomes a big logistical obligation. Physically scheduling a flight, high cost, extended turnaround times. You have to be in close proximity to a provider, or may not be an option. This is why these results, paired with how we can turn around the data and that we're completely remote, is why we've done more surveys of tailing storage facilities than any other organization in the world. Okay, so I'd like to get back to the concept of precision as it relates to survey data. Okay, so why is precision important? Okay, so I'd like to take a look at this example of a survey we did a few years ago. This is a tailing storage facility here, once again, and you can see, there's a lot of checkpoint data in the inactive areas surrounding this facility. Okay, so we did a survey in June, and we determined the June survey relative to the existing survey checkpoint data in those inactive areas had an RMSE, or vertical accuracy, of 11 centimeters, but a mean error of only 1 centimeter, meaning you predict a vertical difference of plus or minus 11 centimeters between the PhotoSat survey and the checkpoint data. However, because the RMSE, the vertical error, is pretty symmetrical in both the positive and negative direction, there's no bias here in the data, the mean averages out to 1 centimeter. Okay, so we conducted a survey of the same facility 2 months later in August. We conducted the same analysis on our work and determined once again we had an RMSE of 11 centimeters. But this time, when you average them out, because of the symmetrical nature or the symmetrical distribution of the error, the mean error this time is 0 centimeters. Okay, the difference in mean error between the June survey and the August survey creates the offset value. The lower the offset value between the two surfaces, the more consistent your data is, the higher the precision. In this generic example on your screen, you can see you have a negative skew 1 month of the data and a positive skew the other month of the data. This is creating a large mean offset value, which is, reflective of inconsistent data. However, looking back at our example, we had a mean error in June of 1 centimeter, a mean error in August of 0 centimeters, of 0 centimeter. So the offset value in that situation is 1 centimeter minus 0 centimeters, so 1 centimeter. So very consistent data. Okay, so why is this important? Okay, you can see here a volume error predictor formula that basically states, based on 4 variables, you can predict the amount of volume error when you run 2 surfaces against each other. Okay, so what are those variables? The area, the surface area of the surface itself, and that's just for scale. Larger the surface, larger the potential area. Then you have E1 and E2, and this is, the vertical accuracy, the absolute accuracy of your surfaces. In both cases, it was 11 centimeters in June, 11 centimeters in August. And then you have that offset value, the difference in the mean error, the measure of precision. Okay, you can see here, this offset value is going to have the largest effect on the volume error you can expect. It's applied directly to the area of your surface. The vertical accuracy is going to play a part, but this entire factor square rooted. The square root of 1,000,000 is 1,000. So, this is going to be applied directly. So the offset value, the consistency of your data, is going to affect your volume error, in the most significant fashion. And this, you're comparing surfaces, the relative difference is what's important, not necessarily where it is on an absolute basis. Okay, so let's take a look at this tailing storage facility that we were referencing earlier. Okay, this tailing cell here, 800,000 square meters in surface area, E1 and E2, the RMSE, 11 centimeters in both situations. We have an offset value of 1 centimeter. Okay, when we plug those numbers into the formula, we can see we are anticipating a volume error here of 8,000 cubes. Okay, 8,000 cubes, obviously a lot of material in real life, but given the size of this tailing cell, it's probably something you can live with, especially given how thin this tailing cell appears to be. But you can see here, once you get to high offset values, 10 centimeters, 25 centimeters, 50 centimeters, it doesn't take very long to get to massive volume errors. you know, you get to six figures very quickly. And this is definitely going to compromise your planning. It's going to compromise your operation, and it's not something you can use. Okay, another example here to quantify the issue. Okay, you have this large waste dump, this time, fairly thick. 500,000 square meters, 11.6 million cubes if you go from base surface to top surface. 2 centimeter mean offset, 10,500 cube error. But you can see once again, it doesn't take very long to get to six figures in volume errors. 10 centimeters, 20 centimeters. At 50 centimeters, you're looking at 261,000 cubic meters in volume errors. And that's massive. Even for a large operation, that would be, probably a day of waste production. Okay, so it's really important that your survey data is not vertically offset, that you keep those mean offset values low, because you're going to get really large volume errors. And vertically offset survey data is really common, which brings me to my next slide. Okay, so when we're getting ready to the first survey of a client site, we're going to ask them for old survey data, existing survey data. We're going to take that older survey data. We're going to look for survey data in inactive areas, and we're going to use that as control to register our survey. We would say in about 80% of the data that the clients supply to us in that initial survey, there is some component of it which is vertically offset, and it's often hiding within a larger data set. And we kind of have to, uncover that as we go. Okay, so to represent this concept, I've chosen this kind of split view here. On the left, you're going to have a plan view map. Nothing complicated there. Top of the page is north, bottom of the page is south. These X's, those red dots, that represents survey data that our clients sent to us that we're going to use, to register our survey. Then on the right, it's an elevation difference variogram. Okay, the X-axis is the northings, so you can locate these points in space. These 3 points here to the south, these 3 points here to the south, these 3 points here to the north, these 3 points here to the north. Okay, and then on the y-axis is an elevation difference. Okay, it's an elevation difference of, let's say, this point as it was supplied to us initially versus what our survey date or what our surveyed surface showed it to be in the end. So there's a statement here that the distance from the x-axis here or along the y-axis is essentially error in the survey data that was supplied to us. Okay, so what we have here is a very common situation. You have basically 4 different types of data sets, and 2 of them are vertically offset. One negatively 70 cents too low, and this one to the north clearly 60 cents too high. These 2 are pretty good, but this gets clustered together and it kind of compromises the validity of the entire data set. Okay, another example here. So we're getting ready to produce a new survey surface for a large open pit mine. They're going from the development phase into the operational phase. They want a new, more accurate topographic surface, original ground surface to work off of. So they send us their drill collar data, and we're going to use that information to register our survey. So we take that drill collar data, we produce our initial surface, we look at the control they sent us, and it looks a little something like this. So there's obvious clusters or groupings here of survey data that was picked up at different time that produced, different vertical offsets. These are pretty glaring, 70 cents too high, 170 centimeters, 2.2 meters. The data set to the far east, actually pretty good, but, it gets merged in with the rest and it kind of compromises the whole thing. In this particular situation, it was, I think, very important that they came to us at this stage to produce a surface. We could flag these issues with their drill collar data. This drill collar data is going to be used to inform their block model. You don't want your block model to be offset vertically 2.2 meters. That can be pretty dangerous, especially if you're in a situation where, the ore body is fairly thin. You could be digging in what you think is ore, but it's actually waste. Now you're sending waste to the plant or to the dike. That could cost you millions of dollars down the road. So, an underrated benefit of really working with us is not only, the new survey data that we're going to produce for you, but really our ability to vet your existing survey data and maybe clean up some errors that, may be minor, but in this case might be fairly substantial. Okay, another example here. This one, very common. On the left here, you see in plan view, some survey data of a tailing storage facility they picked up with a drone. And you can see, different flights, smaller data sets, kind of producing, variable quality in terms of the results. Some areas are offset too low in terms of the data. Some areas are offset a little too high 50 cents high, 50 cents low. Some are dead on. In these smaller data sets, they're not going to exist in isolation. They're going to get quilted together into a more comprehensive surface. You're going to run that surface against your capacity level. You're going to run it against your design to figure out material requirements, and it's going to start affecting your operation. You're going to start scheduling too much material to one end of your dike, not enough to the other. Your capacity measurements are going to get compromised. That might start to mess with your tailing line move timing. It's important to make sure when you're working with these smaller data sets that they're not vertically offset and you're not propagating these errors over time. Okay, last example. I know it's getting redundant. So, large open pit operation here. They want a full site surface. We want to produce a new full site surface for them. So they send us a surface of their entire mine grid from a few months back. We're going to use that. We're going to look for survey data in inactive areas, use that to register our survey. Okay, so we produce our new survey. We compare it to the data they sent us, and you can see the variogram is all over the place. But a lot of that is normal, right? This is an active mine site. We're comparing data that is now current to something that's 2 months old. The pit is getting excavated, the dike's getting built up. There's going to be a lot of vertical variation in between points from, a full site surfaces from 2 different points in time. Okay, so we eliminate the active areas from our study. We eliminate the inactive areas that we know are correct, and we're left with, this. Okay, so you have pockets here of vertically offset data hiding within your full site grid, and you don't really know they're there. Okay, look at this area to the west here. These orange, purple, and pink points, they're all adjacent geographically. But there's a 2-meter swing here between the orange points and these, darker purple points. And you would never suspect that if you were working with this surface. And to me, this is a structural byproduct with constantly building up your survey database with many sources, many components, many methodologies. You're creating a lot of smaller moving pieces, and it gets harder and harder to maintain. And every time you add a smaller data set to that, it's another piece. And, eventually something is probably going to go wrong, which is why, you do need to reset your survey database with a more comprehensive surface, something that's one data set. So you're not propagating these errors over time. Okay, so what are the causes of these vertically offset errors? Okay, they can be fairly straightforward. Okay, so here, another variogram from our project that we were working on. Our clients send us some control data. We produce our survey, we look at their control data, and immediately, something's wrong here. One set is 23 cents too high, and the other set is 83 cents vertically offset in the positive direction as well. So what's happening? Okay, well, communication issue. We thought we were getting bottom of survey monument. They sent us the top of the survey monument. And, the vertical offset in this situation was exactly the height of the monument. Okay, this seems probably a little silly, definitely avoidable, but I think this kind of stuff happens a lot. And, if you don't flag it at the onset, and you're using this as a reference, you're going to start producing survey data that is going to be vertically offset for a very long time. Okay. It's also important to know the vertical reference system for the survey for each mine site. PhotoSat frequently receives mine survey data with unknown or undefined vertical references. Often it's not clear if the mine site elevations are ellipsoidal, so relative to an ellipsoidal approximation of the shape of the Earth, or geoidal, relative to a geoid model of the Earth. Elevations relative to an ellipsoid such as WGS 84 can be tens of meters different from an elevation relative to a geoid model like EGM 2008. Elevations relative to different geoid models can also be, different by more than a meter. Okay, this diagram here shows the surface topography in 2 different ellipsoids, WGS 84 and GSR 80, and 6 different geoid models. Each of these vertical references will provide a different elevation for a point at the surface. Okay, this table shows the elevation difference in Ottawa, Canada, my hometown, for 6 different geoid models. Okay, so a perfectly accurate survey with GSD 91 geoid will have an elevation error of 89 centimeters if it's incorrectly labeled as CGVD 28. Okay, you also have to be aware of custom geoids, often described as above sea level. PhotoSat worked on a project in South America in which there were 3 existing sets of survey data, each with over 50 GPS survey monuments. On each survey, the elevations were defined as height above sea level. Interestingly, though, the 3 surveys covered approximately the same area, but none of the surveys included the same monuments, so there was no way to directly compare the elevations. When PhotoSat tied these three surveys together in one comprehensive satellite survey, we discovered that each of the surveys had a different definition of above sea level, and none of the surveys described how they had arrived at that definition. The elevation differences between these surveys varied up to 1.5 meters. So when you see elevations labeled as above sea level or SNMM, and these terms are not clearly defined, you need to beware. Okay, another issue, tectonically active areas. Okay, in tectonically active areas, the World Survey benchmarks often move up to 2 centimeters horizontally and 1 centimeter vertically each year. So 25-year-old survey data can be different by 50 centimeters horizontally and 25 centimeters vertically from a current survey of that same benchmark. So kind of like currency, survey data is often adjusted to a particular year, like Surgus 2016. So all the years are kind of referencing a specific year. So this kind of temporal effect doesn't influence your survey data. Okay, another issue can be custom mine grids. Okay, so once again here, plan view, some survey data, some survey monuments sent to us by one of our clients. Okay, so we're getting ready to the first survey of their site. And we notice immediately, there's something wrong with the transform system. And these transform systems can get pretty complicated. It isn't just about a horizontal and vertical shift. There's a rotation and scale factor component to it. Look how non-intuitive the coordinate relocation appears on your screen. Okay, so these arrows, these distances, this represents what it takes to go from UTM to their custom mine grid. Okay, in the east here, you're going south 6.1 meters. In the middle, you're going west 1.5 meters. And then in the west, you're going northeast 5 meters, non-intuitive. And what often happens is the nature of the transform system might change, or different versions of it exist simultaneously, and that can create a mess. Okay, and that's what was going on in this particular situation. You had 3 different units using 3 different transform systems, but they didn't know the transform systems were different. It's only really through our kind of investigative work in terms of trying to produce a survey for them that we found this out. So we decided we're going to create a new transform system for them, one that's going to work throughout their entire mine site. And that's what we did. You can see it here. Obviously, I've obscured any specifics, but this is a polynomial transform and works throughout their mine. You can see it's not straightforward. Horizontal translation, rotation angles, center of rotation, and a scale factor. They all need to be determined and incorporated into these polynomials. I know at a mine I used to work at, it wasn't quite this complex in terms of the problem, but we had different spreadsheets for what was supposed to be the same transform system to go from our mine grid to UTM. And, we noticed that it was producing slightly different results. At the time we felt it was close enough and we continued to use it. But, after a while, you start to notice that your as-builts aren't quite right and your buried lines aren't where you think they are. And I think, in retrospect, that probably had something to do with the transform system. Okay, so moving on to an ongoing site surveying project that we do, Suncor's Millennium Mine. Okay, so this is Suncor's Millennium Mine, fairly large mine, 271 square kilometers in area. They move over 1 million tons of dirt a day. 400,000 tons of that is ore. That produces, roughly 350,000 barrels of synthetic crude. And they decided at a corporate level, they wanted a standardized, large, continuous data set surface at least monthly. They still use drones, they still use LiDAR scanners, they still use traditional GPS, but they want that to be built based off of reference to a large comprehensive surface. They want at least monthly, and they insist on at least 15 centimeters or better in vertical accuracy on their data, and they do vet it very consistently. And this gives them consistent data for all their departments, tailings, mine planning, major projects. The plant, everybody's using the same topographic surfaces because it does keep getting reset on a monthly basis. Paul Lamont, the head of their survey department, he published a comparison at a Trimble conference, comparing ground surveys, laser scanners, drones, airborne LiDAR, and he decided that implementing satellite surveying from PhotoSat would be industry-leading best practice for them. And they have multiple types of tailings facilities that were monitored for them. You can see, a traditional, at least to me, tailings facility here in the south, overburden dike, beach, pond, mature fine tailings drying cells over here, a dewatered sand dump, and another dump over here, and also, a couple pits, so a lot going on. Okay, this is one of those tailings facilities that we're monitoring for them right now. It is definitely the one that they require the most survey data on from us. This is Sand Dump 8. 4 million square meters, 39 million cubic meters of tailings sand deposited there a year, 74 tailing cells, 74 discharge locations, and it operates all year long. And you can expect in a cell an average vertical displacement of anywhere from 10 centimeters to more than 3 meters per month. And I think this really typifies the utility of our surveys. Okay, you have this large dynamic structure. It's constantly changing, very active. And you want survey data on it on a regular basis to plan against. Okay, so you can't really pick this up by hand. Well, you can't pick it up by hand. You know, it's too big, it's too complex, it would take you too long, it'd be too unsafe. You can't scan it because of its geometry. You know, you'll get the walls, but you won't get the top. You know, and the top's pretty important. I should mention this is a topographic surface here in elevation map format. Cool colors, lower elevation, warm colors, higher elevation, just overlaid over a satellite photo for a visual. Okay, so your other option is droning it, you know, and they've tried that, but then you encounter that issue where you are creating those smaller data sets. They may be vertically offset. It takes a lot of QA, QC work, you know, at the mine level to make sure it's correct. And you don't necessarily have that time because you want to plan with it. Also, you're introducing, you know, an operator flying a drone around an active dump that could create a safety situation, which we know, you know, you're always trying to avoid. Your other option here would be airborne LiDAR, and that would give you the coverage and the accuracy that you need. Now, the issue once again here is turnaround time. You know, they need something they can use for that week's plan, for that 2-week plan. So this is where we come in. You know, we provide you that airborne LiDAR coverage, that airborne LiDAR accuracy, but we turn the data around quickly because this is such a recurring project. After we capture the data, we can turn around in 48 hours. So, you know, they have current survey data they can work with. Also, everything is done completely remote. You know, no boots on the ground, no flights to schedule, no passes, no testing. You know, it's not as if we weren't there. We're not there, but you still get your data. You get it back quickly. Okay, so this slide's taken from a presentation the head of their survey department did at a Trimble conference in 2014. So they wanted to evaluate the quality of our data. You know, they're obviously not just going to use data from anyone. So, you know, they took a waste dump on a particular day. You know, they used a common base surface, and then they, you know, scanned with a Trimble scanner the top surface on a specific day. They ran the volume from the base surface to what they picked up and scanned themselves, and they got roughly, you know, 78,000 cubic yards or 50,000 cubic meters. Okay, then they compared that to a photosat surface that we picked up on that same day, and we got 77,000 cubic yards. So 1.2% difference overall. Our surface was half an inch lower on average, so 1.2 centimeters. So by all accounts, excellent. And you know, this is why in certain situations, if Suncor Millennium has a dispute with a subcontractor as it relates to payment, and the payment is determined by survey volume, either the cut or the fill, you know, both parties will agree to use us as an independent third party because Suncor knows, you know, we're going to get volume measurements that are right in line with the truth, with what they would get. Okay, here on the left, you see, you know, a satellite photo that we use to produce the topographic surface data. And then on the right, you know, the topographic surfaces themselves. Okay, one thing to note here is, you know, with satellite surveying, you can really customize the survey data that you're getting. You know, this helps you control costs because you only pay for what you know, for what you want, and also helps you manage the data. But this is still one continuous data set. Like, for example, if you wanted to take the sand dump and link it to these cells, so you wanted to process this entire area between, you know, it would match perfectly. You know, there's not going to be that issue sometimes you see with flights or drones where, you know, you're going to fly one area, then you'll fly the adjacent area, and, you know, you'll see where they overlap and they don't quite connect. And even if it's just a little bit, it's a little unsettling because, you know, which one's right, which one's wrong? Is it somewhere in between? That's never going to happen with us because this entire area has been processed. These areas are just clipped out, and this is still one continuous data set. You know, and there's a total of 16 active areas that we're monitoring them for them right now, and they get to pick and choose a la carte, you know, which ones they want month by month. You know, this helps them, you know, manage their data, and helps them, you know exactly when they're getting their data. So one thing here that I think is a really big advantage in terms of satellite surveying versus other methodologies that I've seen in the past is the fact that everything is timestamped to the minute. So first of all your survey data is gathered simultaneously. And there's going to be benefits to that, especially if you're looking to survey reconcile, let's say in your pit. You want to survey reconcile production, either in the waste or the ore, versus what you're seeing in your dispatch database. Well, now you can cut your dispatch database at a specific load because you have your survey data, timestamped to the minute. That's going to give you an extra level of precision in what you're doing. If you have a relationship with a subcontractor where they're invoicing you monthly for material moved, you know exactly when your survey was taken. So you know exactly, how many load counts you're comparing against on their end. That's going to help you control cash flow where, you're not going to be working on a project and then at the end, you're going to get a huge, survey adjustment upwards or downwards. Same thing in terms of a tailings application. The plant's going to have a lot of information in terms of, how much tailings they're producing, how much, has been placed in terms of, water into your tailings pond. They probably have that information, down to a pretty specific, point in time. Now, on the mining side, on the tailings side, you're also going to have that level of precision in your survey data. And, you can, keep the plan honest, potentially, or even just, kind of really study things like maybe water loss in your tailings or, the balance between the waste that you're moving and what's being placed on your dike. Okay, so what do our clients do with our data? They make illustrative cross sections either themselves or from us, studying the evolution of their tailings facility, of the beach over time. You can see here, there really isn't that much thickness in terms of tailings placed over the entire span of this tailings facility month by month, but you can still see it in terms of the detail, in terms of the vertical variation in the topographic surfaces. We produce toes and crests. We've adapted our software to generate these from the surface itself. A lot of clients want toes and crests either on their dike or in their pit. They want the topographic surface, but they want the line work as well. So we can generate that. You can take this to another level too. If you want to start, looking at the compliance in terms of the width of your benching on your road, on your roadways, different things like that, because the line work is generated so quickly, you can use that information in a lot of different ways. Okay, another example here. So this is another tailings storage facility from one of our clients. So they supplied us with the drone data above in terms of the control we were going to use. And you can see here, very quickly, why they came to us. There's a lot of issues here, and this is fairly common. There's probably a gap in the data here for whatever reason. So it's just tinned across. You can see a lack of detail density on the berm here. This also looks like it was kind of just flat tinned across here as well. So, this probably should have been reflown. Not sure what happened that day, but obviously this is going to affect your operation in terms of, if you use it to plan or operationally. And you compare that to the surface we produced, you can see the difference here in terms of the texture of the surface, the granularity. There's no gaps in the data. Everything's very consistent, full detail on the berm, just, a whole different type of product. We could take their drone data and analyze it, and we could see, they had 49 centimeters on average in vertical accuracy. And errors of up to 2.5 meters in spots, even above 2.5 meters. So all in all, not something you can use at this stage to plan in a mining environment. Okay, tailings pond boundaries and water body maps. So in terms of determining, water lines, the location of pooling water, we do things a little differently than maybe a lot of sites. Okay, so what we're going to do is we conduct a spectral analysis on the satellite photos themselves to determine the location of water. Okay, so you can see here above a satellite image, kind of zoomed in, of a tailings storage facility. You can see the dike here, the beach, the pond, and then below, what happens when you filter that through the color bands. So one of those color bands is infrared, and infrared is going to get completely absorbed by water. And that creates a distinct boundary between, anything above and below water. So you can really locate, areas of water on your site. Now, this is taken from, that same client. They had two really important KPIs in terms of their tailings storage facility. One was beach length. The other was the area of the supernatant pond. Both of those KPIs require you identifying, your water line, where the water is. They were initially using a drone operator. And, depending on who they sent to site to survey the area, it was creating very variable results month to month. So it got really difficult for them to track it. So they scrapped this system. They went with the spectral analysis. They've been using that for a few years now, and it works well because, it relies on, artificial intelligence, machine learning, it's not a subjective process. It's a very objective process. So it's very consistent and very accurate, which is what you want when you're tracking something. And this is going to be applied in a few different ways. So for example, in climates like Canada, in these large open pit mining operations, you're going to have a lot of, smaller sump type areas, a lot of areas where pooling water is just going to kind of organically start to develop over time. It's going to be very difficult to look at a satellite photo and really pick out where these areas are. It's not like the water is going to be bright blue. And these areas, they're going to freeze over. They're going to get lightly covered in snow, and they're not going to be visible to anybody driving, around your pit in a pickup truck. These areas are probably also not going to have the bearing capacity to withstand a pickup truck, and people, will fall through, have lost their lives. It's definitely a situation you want to avoid. So, we're going to use this technology to pick up on all these smaller water bodies, provide that to our client. They're going to put that into their hazard map. They're going to flag them in the field if they need it, and, hopefully really avoid these situations. You can apply that to your tailings pond here. Not only picking up on areas of pooling water within your tailings pond that, kind of just look like tailings from a standard satellite photo, but, you can look for areas downstream. Like, do you want water to be pooling here? Is this something that you expected? Is there depression in topography, or is there something, is there an underlying issue that you want to investigate? That just helps, with your planning. Where's my tailings above water? Where's my tailings below water? How does that affect freeboard? Use all that information to kind of inform your planning. You just see it here, areas of pooling water overlaid over the topographic surface. And then here, just, kind of a final comparison of, the drone photo versus, a high resolution satellite photo, and the survey it produced versus obviously an issue here. This isn't really fair. This should have been reflown, but, they still used it to process a survey. And, you can tell just basically just a giant gap in the data that they turned across. Okay, I just want to touch on dam breach analysis quickly. Obviously, this isn't, necessarily an application for an active mine site or for tailings planning, but it is related to tailings in a lot of ways. So, definitely with the direction of the industry, you want to assess the consequence of failure of your tailings storage facilities. And this is leading to a lot more dam breach analyses. So these dam breach analyses, they're going to require, survey data in these tighter corridors for, very long extents. So, you're going to have to go many kilometers, potentially thousands of kilometers in a narrow corridor. So there's a couple of ways you can gather survey data for this kind of application. You could use, something like SRTM, publicly available free survey data. That's an option. Obviously, the cost is good, but it's free for a reason. These surfaces have, errors of 10 meters, 20 meters. It's going to compromise your entire dam breach analysis. You're going to get results that are not going to be realistic. Okay, your other option here would probably be airborne LiDAR once again. But it's going to be difficult for a plane to fly in a tight corridor like this. So you're probably going to be paying for a huge swath of data, a lot of it that you don't need. And airborne LiDAR is probably, depending on where you are, you could be beside an airport or something, but depending on where you are, is going to be more expensive per square kilometer regardless. This is why satellite surveying is really, really well adapted to this type of application. You can customize the survey data area that you want. You can customize the satellite photo area that you want. So you can really restrict what you're going to pay for to what you need. So that's really going to help you control costs. Also, and we'll touch more on this in a second, but you can dip into the archive of satellite photo data. So there exists an archive of satellite surveying data that exists out there that you can utilize. Anything over 90 days old is considered archive. So it's already available, so you don't have to wait for it to get captured. You can process it immediately. It's also archived, so it's cheaper than even new satellite photo data. So once you pair the ability to kind of restrict the area, the cost savings from either using archive or new survey data from satellite imagery, you're really starting to lower the cost here. And speaking with clients all the time, once they find out what we can do in terms of producing survey data like this versus their other options, it's definitely really beneficial. So I advise anyone, if you have a corridor type project on the go, contact us, request some pricing, because I think, it's really going to help you in terms of managing your costs. yeah, so we'll take a satellite photo, produce that bare ground surface that you need, hydro enforce it so it works well in your DBA analysis, digitize the buildings, the roads, stream beds, provide that to you as a comprehensive package. Okay, so I'd just like to conclude with, a case history we did probably a couple of years ago now, where we recreated the history of construction and tailings deposition of a tailings storage facility in the Zambian copper belt. So we really wanted to evaluate, what you could do by blending new and archive satellite photo data. We chose, the Mopani copper belt because it reproduces an area, climatically that's not too arid but not too wet. So in terms of, capturing satellite photo data, it's pretty standard. Okay, so our TSF of interest is the active tailings dam to the south here, the Mufulira tailings dam. You can see it here in this WorldView 3 March 23rd, 2020 satellite image. Okay, so the first thing we did is we took that stereo imagery and we produced a new topographic surface, of the entire area. A good starting point, you always need a new surface. It also gives us a lot of, survey data in inactive areas that we can use for reference. But, we're trying to evaluate the history here. So at the very least, we need, an original ground surface, but this facility, started in the 80s. So there is no existing topographic surface available unless, you go into the archive and you try to see what's available. Okay, so based on our analysis, we found 315 cloud-free archive satellite photos since 1967 of this area. Now, a lot of these are shot in stereo, from the two perspectives, so we can directly produce topography, but I would say most of them are shot in mono. So, you can't directly produce topography from them, but you still have hundreds of satellite photos, over time since 1967 of this facility that you can study and use and really inform the construction history. Okay, so the earliest stereo imagery that we found was from September 22nd, 1967. You can see it here, this keyhole spy satellite photo. It is grayscale, but you can tell, even though it's from 1967, it's really high quality, and this is because, it's government technology. So we took that September 22nd, 1967 stereo imagery and produced very accurate topographic surface there that you can see on your right. Once again, elevation map format, so cold colors, lower elevation, warm colors, higher elevation. So you can see here the valley that they initially used to pour their tailings. Makes sense. You have that natural containment. Okay, and then from there, we blended, the topographic surfaces that we could directly produce from the stereo imagery and the ones that we could construct using all the information from all those satellite photos that we could see over time. Okay, so some of the photos, once again, could be produced directly, and others had to be engineered, reconstructed. And I'll just walk you through that process right now. So let's say you're in 1989 here. This image is from 1989. You don't have stereo imagery that you can directly use to produce topography. However, you can see all these different geotechnical boundaries. I can see where the pond is, where the tailings are, the crest, the toe of the dike. I can overlay those features over the original ground surface. Suddenly now I have X, Y, and Z on my pond, on the dike, on the tailings itself. I can model them and then overlay them over the topographic surface. So for example here, you're just starting with, your keyhole 1967 surface, 1 meter contour base here. And I'm just going to overlay the dike. I know where the crest is. I know where the toes are based on my analysis of the satellite imagery. I can run the volume here and I can determine it's 546,000 cubes placed. I can take the footprint of the pond itself, overlay that over the topographic surface. I know where these points are contacting. So now I have an elevation on it. I can see that that's at 1,223.5 meters in elevation, and then reverse engineer the tailings to create this, topographic surface, reconstructed, re-engineered from the satellite photo data, combining that original ground surface with the mono imagery, and then you're getting a lot of detail. I know how much tailings was deposited. I know, how much was placed in the embankment structure, the elevation on the pond, and then from there, I can continue that process into 1990. This is 1989. This is 1990. I can tell there's an extra, 4 million cubes of embankment and tailings material placed. You can see, the pond elevation went up about 2.7 meters. You can see the footprint of the dike expanding there to the north. And then 1992, get that iterative change in volume, that elevation change on your pond. Then you can jump to 2000 here. Looks like the operation slowed down a lot, because you only have 4 million cubes placed from 1992 to 2000. And a lot of this, it requires further analysis in terms of, how much tailings is below water, how much tailings is above water. But that's something that you can now at least do because you have all this information. You're retroactively producing a 3D model of your tailings facility and seeing how that lines up with your planning. You go to 2010 now. Now you're directly producing a topographic surface. You can see the tailings here. You can see the pond. 14 million cubes placed there in that 10-year increment. And then here, finally, 2017 as well. Once again, you've segregated the dike, the tailings, the pond from itself. And now you're retroactively kind of, building a tracking system, a reporting system that you would like to put in going forward. So you can have full continuity for these legacy, for these older facilities. And you're using the detail in the satellite imagery in your analysis as well. You can see, what pour points are active. When are they active? When are they pouring fine tailings? When are they pouring coarse tailings and putting lifts up on their dike? You're putting all this information together and putting it into this study. And then, you can produce any type of drawings, any type of analysis you want, because you now have all that topographic surface data. You can see here a cross section through the dike. You're really reproducing, monitoring, tracking the evolution of the retaining structure itself, of the tailings, of the pond. You can see here the original ground surface in pink below. But not only that, because you have all those geotechnical boundaries, because you have that full analysis, you can create this type of stratigraphic cross-section where you're monitoring the evolution of the fine tailings, of the pond sediment over time. You can even see, the configuration of the starter dike from 1987, and, kind of some infrastructure they placed downstream, probably for drainage. And then you can reproduce the drawings that are important to you. Is beach length of interest? You want a, volume table that's tracking pond heights, yearly placement rates, embankment and tailing volumes over the years. And, the final product is really a full construction history report, with the survey data to back it up, all the technical details, the dike levels, the water heights, the tailings heights, whatever you want to focus on, you now can, because you kind of have a second chance at getting the as-built you need, at getting the information you need. Okay, so I'd like to thank you all for joining me. That kind of concludes the presentation portion of this webinar, and I'll leave the floor open to some questions.
Perfect. Thank you so much, Sam. So we have a few questions. First question is from John Clark, and his question is, how is your technology applied to designing erosion and sedimentation control plans for large mine sites?
Okay, so how is our technology applied to sediment erosion control plans? Well, it really, any type of significant movement down to, more than 10 centimeters on any type of structure, you're going to pick up on that in the topographic surfaces as well. Now with the ability to go back in time and look at, how it looked 5 years ago, 10 years ago, you can really monitor the evolution of that erosion, for a particular facility. So really, it's just about getting high quality survey data, either current or going forward, monitoring on an ongoing basis, or going back in time, and seeing the evolution that you've kind of already reached at this point. So I know, okay, that's probably not a very detailed answer, but it's kind of the best one I can give you without looking at that specific project. But really, you're producing high level topographic surfaces. You're not really bounded by, time. You can go back and then you can kind of tie that all in together to see what kind of movement you can see going back and forward.
Great, thank you. Second question is from Nelson, and his question is, which are the considerations to take into account in winter or in summer to acquire the information? And then follow up, are there some variations in interpretation?
Well, the biggest thing to consider if you want satellite surveying is cloud cover on your site. So, there's certain areas of the world that really have persistent cloud or have really persistent rainy seasons. And that's going to limit our ability to capture survey data. It's not going to prevent it, but it's going to limit it. So if you're in an area of the world and you have a really pronounced rainy season, really pronounced cloud, and you want, let's say, 2 surveys a month, 3 surveys a month, 4 surveys a month, that's going to be hard to pull off. In a lot of the areas of the world, though, that isn't a concern. In terms of, snow cover, yeah, so you're probably more interested in a bare ground surface, right? You don't want to top a snow surface. So if we survey your area initially in the winter, we're going to get top of snow. So, if you're looking to do something detailed, something where you really want accurate volumes, I would recommend getting your initial surface in the summer. So at least then we know exactly where the bare ground is. So then going forward, when we're producing surveys for you in the winter, and let's say some areas are covered in snow, at least then we'll know based on our old survey data, based on our old control data, basically that we've gathered, what thickness we're dealing with in terms of snow.
Perfect. Thank you, Sam. A question from Matthew Cohen, and his question is, precision between 2 surveys over a few months, taking into consideration that elevation on the ground could have changed over time. That's the question. I'm not sure what exactly it's asking. If you can elaborate, Matthew, on your question. Another question is, what is RMSE?
Oh, root mean square error. So it's the standard deviation on the residuals between the new survey we produce and an absolutely known survey in inactive areas. So, when survey companies quote the vertical accuracy on their product, it's an average of the standard deviation on the residuals between, the new survey and something they know is correct.
Okay, thank you. Another question from John Clark. How is your technology used for mine environmental assessment processes?
For mine environmental assessment processes?
Yeah.
Okay, well, I'm not an environmental engineer, so I need more insight into exactly what you're trying to investigate. So, it's kind of up to you what you want to use the survey data for. Really, you're getting a topographic surface. You're getting the ability to do a spectral analysis on the photo to determine areas of water. You're also able to do an alteration analysis on the satellite photo to determine the presence of specific minerals, in exploration type projects. In terms of an environmental analysis, I think there's multiple things you could do. I think you're definitely trying to determine, the location of maybe stream beds or different things. But yeah, I would need a little more information in terms of exactly what you're trying to get accomplished before I can properly answer that question.
Perfect. A question from Dave Sims is, how does topography ruggedness affect your precision and accuracy?
Did you say ruggedness?
Yes.
Yeah, so obviously, areas that are flat are going to be easier to survey. If you're dealing with an area that's like, just a straight vertical drop, if you're off by, a centimeter in X and Y, it's going to have a huge effect on your vertical accuracy. So, areas of terrain that is particularly jagged or rugged, it is going to affect the accuracy of your survey. I think that's true of any methodology. We're accurate to 10 centimeters over distances of 10 kilometers in X and Y. So, we're doing as well as anyone in that regard, as opposed to maybe, surveying it by hand. But yeah, the variability of your topography is going to affect the survey accuracy, but I think that's true of any application.
Perfect. And also follow-up question from Dave Sims is also, how does vegetation affect your ability to survey accurately the land surface below the canopy?
Yeah, so tree cover will affect the survey accuracy. So, high brush, grass, sparse vegetation isn't really going to have that big of an effect. But if we're talking about a jungle, something with really tall trees, persistent tree cover, you can't see the ground, there are no gaps. Then you're looking at something like, probably 10% of the height of the tree canopy cover will be your vertical accuracy, because, you can't see the ground. In those applications where you're dealing with like a dense forest, really dense jungle, that's where airborne LiDAR will probably produce better values, but they're also going to struggle, with that type of vegetation. And as well, then access is going to become an issue because you're going into an area that is, undeveloped. It's probably an exploration situation. So you kind of have to balance your needs there.
Thank you. It looks like we are at the hour, but there are a few more questions coming in. So if you guys have an extra 5-10 minutes to spare, we will stay on for a few more minutes and answer questions. If those that want to leave, I can do the closing remarks now and we can stay on an extra 5-10 minutes. So I want to thank everyone for attending today's webinar. Thank you so much for sharing your knowledge, Sam. Thank you to PhotoSat for this. In a few minutes, you will be receiving a survey from myself. If you can please take out some time to answer those and give us your feedback, it will be greatly appreciated. So thank you. And yeah, we will stay on for a few minutes just to answer any more questions. So a few more questions for you, Sam. Thank you for your contribution. When you compared satellite monitoring with other monitoring tools, could you describe the pros and the cons?
Okay, well, I guess the comparison or what gets confounded the most is, INSAR and our satellite surveys. So INSAR is, an early detection kind of warning system where it is, monitoring spikes in velocity of material over very small distances. So really, it's telling you, this area is moving a lot faster than it should be, and this is kind of a precursor to failure. We produce topographic surfaces that you use to monitor, volume deposition, the evolution of your facility over time that you use to plan off of a design. So it's really two different applications. When people try to produce topography from, I think, the data they get from INSAR, it doesn't work, or it doesn't. I know there's a lot of issues there. I don't know if, they're getting very accurate elevation readings. I know a lot of people try to do both, but it doesn't seem to work. So it's really two different applications. In terms of other, monitoring technologies, we kind of cover them over the course of the presentation. You can drone your facilities, you can airborne LiDAR them, you could try to pick them up by hand. It really is going to depend on scale. As the areas get bigger, you're going to probably need to move away from, these kind of more handheld application or handheld uses like droning. And then you start to encounter situations where the turnaround time on your data, if you want airborne LiDAR all the time, is a little too slow. So I think we're really a nice blend of, high quality accuracy and speed. And, just from a pragmatic point of view, the ease of the process, there's not that much work on our client's end to get this data back. We really just need old survey data, a purchase order, and the timing that you want. And then, we can really give you the information you need.
Thank you. Jonathan Gray wants to know, is your software able to remove tree canopies?
Yeah, we edit out the tree canopies. We're providing bare ground surfaces. So we edit out all of these features that don't reflect the bare ground.
Okay, thank you. Terrence wants to know, can this be used for large scale mapping and creation of LIDAR comparable DSM/DTM of smaller anthropogenic features such as mine shafts, adits, and associated waste rock dumps for abandoned mine land inventory purposes?
Well, yeah, that's interesting. I'd like to take a look at that further, in more specific detail. So if you want to reach out to me at sam@photosat.ca after this presentation, maybe give me a little more specifics as to your project. But definitely from what I heard, I definitely think we can help.
Perfect. Maddie Madison wants to know, how does the snow and the varying albedo affect survey measurements?
Can you define the word albedo, please?
Okay. Mara wants to know, is this technology has been extended, or has this technology been extended for bathymetric survey?
Yes, we do provide shallow water bathymetry in certain applications. It's going to depend on the turbidity of the water in terms of how much we can penetrate the water surface to find that top of tailings below the water. We have some clients, they do deep water bathymetry. So they're going to use what I believe is radar to pick up on the top of tailings in their tailings pond in these deeper areas. But there's always going to be this kind of in between area where it's too shallow for a boat, but it's still below water. And that's where we can potentially penetrate the water surface, pick up at that top of tailings, tie it into our client's deep water bathymetry, tie it into our, above water tailings surface, and then give our client that comprehensive top of tailings surface that they need to really evaluate their capacity.
Perfect, thank you. A question from Mitchell. He's asking, talking about cloud coverages, how is it with vegetation coverages?
Well, yeah, I think, to the earlier question, it really depends on the density, grass, sparse trees, things like that. That's not going to be an issue. If you're dealing with, a forest, untouched forest, there are no gaps in the tree cover, a jungle, there's no gaps. You can't see the ground. That's going to affect your accuracy. And then you can expect, 10% vertical accuracy, or 10% of the tree canopy cover in terms of your vertical accuracy.
Okay, a question from Matthew Cohen. You initially compared precision between two data sets taken months apart. How can you compare precision when there are elevation changes?
Okay, so the precision speaks to the consistency of the data. So what we're using, even though the two areas are months apart, we're looking at inactive areas surrounding the active area. So those areas aren't changing. So even though they're months apart, the survey data, the elevation in those inactive areas is not changing. So there's really no variation there. So that's how we evaluate the quality of our surveys. That's how we evaluate the quality of our surveys generally, because we're gathering such large swaths of data, we typically or always have, large areas of, or large data samples from inactive areas that we can study, that we measure the quality of our survey against. And that's how we avoid, being vertically offset. That's how we avoid a lot of these survey areas, is by always tethering our survey to these inactive areas that surround, the TSF, the mine that we're surveying.
Okay, another question is there any technology that may, I think I asked that already. From Matthew, do you provide data that can be used to measure slope stability and predict slope failures?
Well, what you can do is you can see the evolution of your slope over time. Now, if you're looking for millimeter changes in your slope in terms of, a cross section, it might not appear on the survey. We're 15 centimeters RMSE. So you really need, the evolution of your slope to be kind of at that scale, that 10, 20 centimeter scale, for us to really pick up on it. So I would say you're probably looking at something that's more geotechnical in terms of, measuring your slope. What we can do, though, is we can provide you with topography on your slope on a consistent basis, on a frequent basis, that you can look at, in cross section, in plan view, and kind of study the evolution of it from there. You can also look at the volume differences potentially, on a period to period basis.
Okay, and then we'll just take one more question from John Clark. And his question is, does your technology detect small tailing structures movements to warn of potential tailings failures?
Sorry, could you repeat the question?
Yeah, does your technology detect small tailing structure movement to warn of potential tailings failures?
I would say yes. It really depends on the amount of movement you're looking for. Once again, if 2 centimeters of movement in a specific area on your tailings facility to you is going to predict failure, then that might not be something you're going to pick up on in a topographic surface. And I think that's, true of really most technologies. But if you want to study the evolution of your facility, if you want to look at your facility, once again, in cross section, in plan view, you want a 3D model of it. You want to look at it retroactively. You want to look at it going forward. You want to see the evolution over time. That's where we come in. That's what we can do. But in terms of, spikes in velocity over very small distances, or, really slight variations, over time, that this might not be the right application.
Perfect. Thank you so much, Sam. And thank you to everyone that stayed back for the question and answer period. If there are any more questions, you can feel free to, they can email you, Sam, right?
Yeah, I would encourage, some of these questions where I can tell, there's technical details behind them. You're looking at a specific project you're working on. If you want, please reach out to me, sam@photosat.ca. It's sam@photosat.ca. Provide me with the details of your project. We can look at it together to see if it's a good fit, where we can contribute and potentially, meet your needs. And I'd like to thank you all for joining me today.
Perfect. Thank you so much, Sam. And thank you everyone for participating. This was great. Thank you and have a good rest of the day.